Hello everyone, I'm Jefferson Pardomuan from the Tokyo Institute of Technology. Today I'm presenting our latest work, VabricBeads, a variable stiffness structured fabric utilizing artificial muscle in woven beads. We introduced a novel technique for tuning stiffness in structured fabric, allowing for programmable shapes and stiffness properties. Our approach employs pneumatic artificial muscle discretely integrated within the bead structure. By inflating or deflating these muscles, we can dynamically adjust the fabric stiffness or mold it into predetermined shapes. Furthermore, we explore the design space by altering bead shapes and stitching arrangement to achieve diverse fabric behavior, including drape, stretchability, texture, and breathability. Woven beads, a structured fabric category, comprise interconnected rows of beads joined by fiber strands. Variable stiffness offers valuable capabilities inspired by nature, where animals adapt muscle stiffness to navigate through changing environments. For instance, they may soften their tissue to navigate through narrow space or stiffen their limbs to enhance running capabilities. We envision fabric-type devices adapting stiffness to user tasks or environmental change, augmenting user experience with force and haptic feedbacks. Despite active research in areas like material science and robotics, integrating variable stiffness mechanism into SIGCHI research remains challenging due to its complexity and cost. Vacuum jamming stands out due to its versatility and effectiveness. Within the SIGCHI community, vacuum jamming has seen widespread adoption across the various fields, including the formable interface, shape display, haptic glove, and sheet-type material. Previous research has highlighted the potential of variable stiffness in computer interface, along with the challenge and its implementation. Alternatively, approaches for achieving stiffness variation can include gel-based system, low melting point alloy, and bead jamming. However, none of the prior research has successfully achieved a fabric-type interface with dynamic variable stiffness, straightforward system, and combined with shape-changing capabilities. Our work's central contribution lies in integration between the bead shapes, artificial muscle behavior, and threading patterns. We categorize beads behavior into variable stiffness and shape-changing mechanism. We classify fabric structures into two categories, one DOF and two DOF structures. One DOF structures deform in one direction due to its structural constraint imposed by bead shapes and threading patterns, while two DOF structures deform in two dimensions, vertically or horizontally. Additionally, fabric beads exhibit unique characteristics such as stretchability, permeability, and texture change through scissor and auxetic structures. In this research, we utilize a rotational break mechanism between the beads and artificial muscle to introduce variable stiffness properties ranging from soft and malleable to rigid states. The rotational brake mechanism introduces frictional force to reduce or halt rotational motion effectively. This mechanical feature can be responsively and linearly controlled based on the air pressure in artificial muscle. Our approach leverages the radial expansion force of artificial muscle to generate and manipulate the frictional force on the mechanical constraint, enabling precise stiffness modulation in response to user interaction. In one DOF structures, all beads are arranged in parallel and threaded using the flat period technique. In contrast, two DOF structures involve lining two beads perpendicularly and threading them with vertical artificial muscle in two-channel composition. We further enhance the two DOF structure by applying a right-angle width threading pattern, resulting in more redundant and bendable fabric in multiple directions. Shape-changing fabrics exhibits flexible behavior in soft states, but can be transformed into a predetermined rigid shape when actuated. We incorporate a bead jamming mechanism into the fabric structure, where kinematic and frictional coupling increase when tension is applied. In one DOF structures, beads have 4 parallel holes and are threaded with 2 holes in between. In two DOF structures, beads are threaded with artificial muscle in two-channel composition, allowing for partial actuation. To achieve intricate and curved shape deformation, we explore two approaches. The first involves modifying bead shapes into bead shape, and the second creates slanted beads design. We recognize the critical role of other fabric characteristics such as stretchability, permeability, and texture. Thus, we explore special beads design and arrangement such as scissor and ascetic structures. Scissor structures can transform rotational motion into linear compression and extension, akin to stretchability properties, but without elasticity to return to original shape. The fabric can stretch to become a thin, rigid board capable of holding a 1 kg load when actuated. Conversely, it can collapse into a small but bulky form factor that becomes significantly stiff when actuated. Ascetic structures can be incorporated into our fabric design using flexible TPU as bead material. This bead will bend under the force of artificial muscle, resulting in folding deformation usable in permeability or texture transformation. Fabrication process of fabric beads involve three key components: beads production, artificial muscle threading, and pneumatic control. For beads production, we utilize 3D printing or laser cutting, depending on the desired beads design. Pre-arranging the beads during the design process streamlines the printing process. To achieve dynamic stiffness change, we employ a pneumatic system with high flow rate, enabling rapid actuation for haptic sensation application, achieving cycle under 1 second. Another significant contribution of our research is the exploration of sensing technique integrated into our woven bead structures. Manipulations such as stretching and bending induce fluctuation in air pressure, which can be detected using a pressure sensor. Additionally, a layer of conductive braid shielding allows for capacitive touch detection or electric power delivery. Furthermore, beads can be embedded with range of sensor and electronic components such as velocity and LEDs to provide output information such as stiffness level through variation in LED brightness. To provide in-depth understanding of our fabric's mechanical properties, we conduct technical evaluation, encompass stiffness strength, bending stiffness, scissor structure stiffness, and localized stiffness adjustment. For detailed information, please refer to our paper. We propose 5 types of variable stiffness fabric in our user interface, encompassing wearable device and everyday objects. Variable stiffness wrist-based, beneficial for medical treatment such as emergency case and rehabilitation, as well as for skill training in sports or musical instrument. It mobilizes joint during heavy work, yet allows delicate hand motions such as typing due to its lightweight and flexible design. Variable stiffness glove, suitable for VR applications to simulate various stiffness level of virtual objects, offering unique sensations like ice melting spontaneously. It exhibits linear stiffness variation and can bear loads up to 4 kg. Variable stiffness bag, adjustable to various user needs and environmental change. It can transition from elastic and flexible to rigid box. It offers enhanced protection and stability for its contents. Soft fabric toys, safe and comforting for toddlers, can be transformed into rigid plastic toys with interactive potential for older children and provide durability and stability during play. Shape-changing font, user can bend and fix the font's display to their desired shapes, automatically stiffening to secure itself when wrapped around the wrist, or morphing into curved surface resembling a retro font during calls for ergonomic grips. In conclusion, we would like to discuss the limitation and potential future direction of our works. The reliance on a bulky and heavy pneumatic source presents practical challenges for wearable applications. However, we anticipate overcoming this limitation through the development of smaller compressor or alternative power source such as chemical reaction. Given the current state of development, the most feasible application of fabric beads may lie in furniture and home device. We envision creating large-scale shelters using such fabrics, which can be promptly deployed as needed. Challenges in these regards include automating the artificial muscle threading process and developing computational tools for generating and optimizing structure geometries. Feedback from user evaluation has highlighted issues such as itchiness due to the sharp edge of laser-cut acrylic beads, and slippery surface of beads can be problematic when in contact with glass or steel item. To address these concerns, in future implementation, it is recommended to improve bead design by smoothing edge and coating beads with soft high-friction material like rubber or TPU. The bladder structure inside the artificial muscle is susceptible to punctures. While most of the artificial muscle surface is covered by beads, the exposed artificial muscle loop can suffer from repeated friction with sharp materials, including the beads in themselves. In our current development, we use artificial muscle with 2-layer sleeve to enhance durability and lifespans. In this paper, we present VabricBeads, a concept for variable stiffness fabric utilizing simple artificial muscle and bead structures. Our main contribution lies in the integration of beads constraint and threading pattern to diversify the fabric mechanical properties and deformation behaviors. We have designed VabricBeads in the simplest form, aiming for mass production at a low cost. Although manual threading work is required, we believe our technique opens up new opportunities and paves the way for a new generation of fabric thread products.